Everything is relative. Top 10 Misconceptions and Misunderstood Concepts in Special Relativity, number 12. Everything is relative according to relativity. The common misconception, number 12. What does this mean? Related misconceptions and other possibly faulty ideas. Special relativity is about the fact that motion is relative. Since motion is relative, everybody can view themselves as stationary. According to special relativity, everything is exactly the same relative to any inertial reference frame that we use. Special relativity is about relativity of nature, e.g., hot and cold are relative. And even time is relative, motion is relative, and space is relative, etc. And pretty much every essential concept in special relativity is often misunderstood by many people, to a certain extent. Everything is relative, just like motion is relative. If I move in one direction with respect to you, then you are moving in the opposite direction with respect to me. Of course, that is relativity. Or is it? The phrase, everything is relative, is often used with the more or less same meaning with nothing is absolute. But either way, relativity does not say that. Today, we will primarily focus on the relative part and not the everything part. In particular, we will focus on the concept, motion is relative, since the term relativity in the theory of relativity originally came from this concept. So what do we mean by relative in relativity? The theory of relativity is about? Well, it's not about relativeness or even relativity. But definitely, it has something to do with relativity. This term is used everywhere to describe pretty much every essential concept in special relativity. For example, motion is relative. Distance is relative. Simultaneity is relative. Time is relative. And of course, relativity is based on the principle of relativity. So what does relative really mean in the context of special relativity? First, what does relative mean in common English? In English, the word relative can mean many different things, but here are three most common meanings via examples. Hot and cold are relative. Is 50 degrees Celsius hot or cold? Of course, it depends. It's hot compared to 40 degrees. But it's cold compared to 100 degrees. Is stealing bad? Well, that's relative. In the town of thieves, stealing may be normal and may even be encouraged. In most other places, however, stealing is considered bad. This is called relativism in philosophy. Some people seem to view the world as us versus them. But that's really relative. The designation us refers to us when viewed from us, whereas the other side will see themselves as us and us as them. In all these examples, the common connotation is that the relativeness relationship is somewhat symmetric or reciprocal. That is, for instance, if we say A is hotter than B, then it automatically implies that B is colder than A. When people say everything is relative, these are the most common meanings. Obviously, this is not the case in relativity, since we are elaborating on these common meanings of relative in English. The most common meanings of the word relative in English usually imply mutual relationship as well. Or they tend to have connotations of symmetric or reflexive or reciprocal. By the way, texts that are too small or too dim to read are not meant to be read. For instance, using the previous example of hot and cold, here's an illustration of relativeness. The two statements, Bob is hotter than Alice and Alice is colder than Bob, describe exactly the same mutual relationship. In the conventional meaning of the phrase, motion is relative, this reciprocity relationship is also implied. If A moves at speed v relative to B, then B moves at speed minus v relative to A, and vice versa. The conventional meaning of the principle, motion is relative, from classical mechanics, also has this connotation of reciprocity. In fact, this is the meaning that most people, even experienced relativists, think of when they hear this phrase, motion is relative. But that's not what relative really means in the theory of relativity. Is this the greatest blunder of Albert Einstein and Max Planck? It was said that Einstein referred to the fact that he added the cosmological constant to his gravitational field equations as his greatest blunder. But there is no record of him saying that, as far as we are aware. This particular expression is attributed to George Gamow, as in hearsay, who was one of the earliest proponents of general relativity. The term relativity in the context of Einstein's theory of relativity was first coined by Max Planck. Einstein himself started using this word to officially refer to his theory at around 1910. In his later years, however, he had some qualms about the use of this word relativity because of its association with various common meanings in English, as well as in many other languages. In particular, he hated the fact that some philosophers, who were rather ignorant of the theory of relativity, used the theory to support relativism in philosophy. If you think that the theory of relativity is about such relativeness, then you are misunderstanding the theory of relativity. By the way, it's not about the name, but definitely the names used for particular concepts influence how these concepts are first received by people who are new to them. In fact, another related item with the same general theme is also in our top 10 list. The Principle of Relativity. Let's start from the absolute basics. Special relativity is ultimately built on top of one fundamental principle, namely, the Principle of Relativity. The Principle of Relativity states that physical processes follow exactly the same laws of nature in every reference frame. We are not going to explain what the Principle of Relativity is today. Most viewers must at least have heard of it. But more importantly, the principle of physics. The Principle of Relativity is based on a few other more fundamental principles. For example, we describe physics relative to a reference frame, and in particular, relative to an inertial reference frame, in the context of special relativity. That is, physics is relative. An inertial reference frame is a reference frame that is in a uniform translational motion. Physics is relative? As Einstein stipulated, some 120 years ago, that not only the motion of a body, that is, mechanics, but also all physics has to be described relative to a reference frame. This is what we mean by physics is relative. Or in other words, physics is to be understood relative to a reference frame. This seems, in a way, even more fundamental than the Principle of Relativity. The Principle of Relativity would not be a universal principle if this prerequisite did not hold, that is, if physics would not have to be described with respect to a reference frame. And yet, nobody doesn't seem to pay much attention to this fundamental principle. Now, what do we mean when we say that motion is relative in relativity? Although the conventional meaning is not wrong, it should now be interpreted in the sense of relativity. The motions of bodies, e.g., B, C, can only be described relative to another body, e.g., A. Note that the relationship between the describee, say B, and the describer, say A, does not have to be symmetric. Clearly, the motion of the body B, in this example, can also be described relative to the body A. Hence, the two descriptions of A with respect to B and of B with respect to A can be symmetric. In fact, if A moves at speed v blank AB relative to B, and B moves at speed v blank BA relative to A, then v blank AB equals minus v blank BA. But although this is a very common scenario, it is somewhat incidental. This is more of an exception than a rule, as far as relativity is concerned. The paradox of relativity. Now, a lot of puzzles in relativity, which seem to you to be paradoxes, no longer appear to be so when you adopt this new interpretation of the word relative. For example, the paradox of time dilation. If A's time runs more slowly compared to B's time, shouldn't B's time run faster than A's time? Isn't that relativity? Well, no. The paradox of length contraction. If A's measuring stick gets shorter compared to B's measuring stick, shouldn't B's measuring stick be longer than A's measuring stick? Isn't that relativity? Well, no. The unit time of B when viewed by A is T-BA. The unit time of A when viewed by B is T-AB. These are defined with respect to two different reference frames, and there is no reason why T-BA should be the same as T-AB. The same holds for length contraction and all other relativistic phenomena. To conclude, relativity is, first and foremost, about the fact that we describe physics relative to a reference frame, and it is not about the relativeness in the common sense. Physics is relative. You see the world from the point of view of an observer. We often use the term observer in physics, and it does not necessarily refer to a human observer. In the context of relativity, an observer is often synonymous with reference frame. Let's start from some philosophy. The Copernican Principle. All physicists and physics students must be familiar with the so-called Copernican Principle. In physics and related disciplines like astronomy, this principle states that we humans do not occupy any special place in this world. That is, for example, we are not at the center of the universe. In philosophy, however, it has slightly different meaning. In fact, the term the Copernican revolution was first coined by Immanuel Kant in the context of epistemology, philosophy of knowledge learning. For Kant, it was a revelation. Traditionally, we almost always saw the world from our own eyes. The fact that people, before Copernicus and Aristarchus, thought that the Earth was at the center of the universe was almost incidental. It was just a part of the bigger picture. Kant ultimately realized that we possessed an innate ability to see the world from the perspective of other people's eyes, and not only from our own viewpoints. In case of Copernicus, he was able to describe the world from the viewpoint of the sun, somebody else, rather than from the Earth, us. This is what Kant called the Copernican revolution, that is, the human ability to think from other observers' perspective. Now, everybody knows what an inertial reference frame is. Let's consider this concept from the perspective of the Copernican principle, in the Kantian sense. This is one of the most important ideas in special relativity, and in physics in general. According to special relativity, we describe physical phenomena with respect to an inertial reference frame. In general, we describe physics with respect to a reference frame, although this is not always explicit. Again, this is what we mean by physics is relative. Each of us always carries the me reference frame, e.g., attached to my head. We can also see the world with respect to other reference frames. Now let's have a second look at the dictum, motion is relative, from the perspective of the Copernican principle, in the Kantian sense. Now, circling back to motion is relative, we describe the motion of a body relative to an inertial reference frame. In fact, we describe any physical phenomena in general relative to a reference frame. Although we can view any rigid body as a reference frame, as we emphasized, the describee-describer relationship is not symmetric. The recap of what we have learned for the last 10 minutes of our life. We describe physics relative to a reference frame. This can be viewed as a realization of Immanuel Kant's Copernican principle. In physics, the word relative can be understood in two slightly different ways. First, physics is relative to a reference frame, as we just discussed, and second, there are certain things that are not universal, which all viewers already know. We tend to emphasize the relativity of these things. In fact, very few things are relative in our universe in the second sense. All laws are the same with respect to reference frames, that is, the principle of relativity. Space, time, and motion are relative according to the special theory of relativity. And electricity and magnetism are also relative according to Einstein. Again, to emphasize, all physical laws with respect to any inertial reference frames are the same for all of us, according to the principle of relativity. It's somewhat ironic that we emphasize the relativity of these small set of phenomena, albeit rather important, than the universality of the laws of nature. What's next? Do you really understand the law of physics, that the speed of light is constant? Motion is relative, and the speed is relative, and yet light always propagates at the same speed to everyone. How is that possible? This paradox puzzled young Einstein, which ultimately led him to his discovery of special relativity. Unfortunately, there is still so much confusion remaining about this fundamental, albeit rather strange law. For example, many popular science communicators, such as Brian Cox and Neil deGrasse Tyson, among many others, make statements that are not consistent with this law of constant speed of light, likely indicating that they do not understand this law at the intuitive level. In the next episode, number 11 of our top 10 misconception list, we will address this law. Take-home questions. What is the one thing that you learned in the last 10 minutes of your life? What was your understanding of reference frame before watching this video? Having watched this video, what is the reference frame in your view? What is the Copernican revolution, according to Kant? Do you think that the Copernican principle in cosmology is really a principle? When someone says to you, everything is relative according to relativity, what would you say to them? What does the statement, motion is relative mean to you? What does the statement, time is relative mean to you? Why do you think anybody should care about special relativity? Please like and subscribe Nutty Physics.